Hey everyone. So this is another video I want to get out for you guys. Unfortunately, I missed one class's exam, but for everyone else, I'm hoping that this video helps review and go over some of the things that you'll see on your exam. Um, and I'm going to assume that you've already seen the first video, so I'm not going to go over things like for loops and if statements. I'm just going to assume you know how they work. If you don't, I highly suggest checking out the first video and then also looking at lecture notes from your professor and things like that. But otherwise, I don't want to take up too much time. I only have a few things to go over this time, so hopefully this video should be a lot shorter than the previous one. And yeah, let's just jump straight into it. So the first thing I want to go over is switch and case. So some people went over this relatively early. Some people are only learning it now. But at its core, a switch statement is a modified if statement. And the way you use it is you switch some sort of variable, and then each of the cases are like checking for something in an if statement, right? So instead of doing if I equals 1 or if I equals 2, I equals 3, things like that, you can switch I and then check every single case for it. So here I just have you switch a variable and you check for its values, and each of your cases are different possible values. So obviously if you switch an integer, then you check for integers. If you switch chars, you check for chars. If you switch strings, you can search entire words. So here I use a for loop, and that's because I want to show you like every single test case here. And notice I'm putting a break statement after every printf, and this is to prevent something called fall through, which I'll showcase in a second. So if I go ahead and compile this, switch and case, let me go ahead and make this bigger as well. And let me go ahead and comment this part out, just so we can focus at the beginning. So here you can see that this for loop is going from 1 to 5, and it's printing out selection 1, selection 2, selection 3, selection 4, and then invalid number. Invalid number being essentially like the else in an if-else statement. And I said something about fall through. Well, when a switch and case statement is when it goes inside one of the cases, it runs all the lines of code in it, but then it also tries to run the cases below it. And if you don't have those breaks there, you fall through to the next lines. So if I go ahead and run this again, you can see what's happening on this fall through, right? So on iteration 1, it goes into the first case and it prints out all of the ones below. Then for the second case, it goes down and it only starts here, and then the third iteration, fourth iteration, fifth iteration, etc. And you can see here that when we put these breaks here again, we only get the individual cases correctly. Now, switch cases by themselves aren't too helpful, but they're nice for organization purposes and things called menu-based programs. So if I go ahead and uncomment this again, when I say menu-based program, I mean something that keeps running until the user tells it to stop. So in this case, I have an infinite while loop, so while 1, which is always going to be true, and I'm doing switch menu selection. And every single time this loop finishes, I go back to the top and I say enter a number 1 through 3, and then I ask the user, he puts in some number, and then we switch that value he puts in. So here I use continue instead of break, because if I use break, I'd leave the for loop, right? And then I have a special case, so case 4 ends up breaking it, it returns here, and that just officially ends the program. So if I go ahead and I already have it running, so if I do 1 a lot, you can see it just keeps on going and tells me selection 1. And if I do 2, 3, etc., and if I try any other number other than 4, it tells me invalid selection number, and as soon as I type 4, the program ends. So this is helpful in long projects that you might have for organization purposes. I think switch statements are a lot cleaner than if statements, but they also are a lot bigger in terms of code bloat, because you do have to write these breaks and continues constantly. So it really just depends on the coder who wants to, what they want to do with the code. But I think at its core, switch statements are pretty easy to understand, so I'm not going to spend too much more time on it. And we're going to go over to one of the more harder topics, which are pointers. So pointers are variables that hold memory addresses as opposed to holding some other value. So like when we create an integer, we know it has to hold some sort of integer value. Well, in pointers, they have to hold addresses to their specific data type. So an integer pointer holds an address of an integer. And then by dereferencing that value, we can change the value inside of the local variable. And dereferencing essentially is just a fancy word for saying going to the address that it holds. So here, the way to dereference is you do the star symbol and then the name of the pointer, and then you can just treat it like it's the regular variable, right? So when we're dereferencing pointer here and we're setting equal to 5, that's the same thing as just saying a equals 5. So go to the location that pointer holds, address of a, and change the value inside of it. So we're changing it to 5. I'll keep that there and put same thing. And here I have like a little diagram. So here I have a is located at 1, 2, 3, and it holds 0, and pointer holds its address, and then I can change the value in pointer to change the value in a. So that's just a nice diagram, I think, for you guys. And I have some more examples here. Yeah, you can also do it on one line. You don't have to do it on multiple. And then variables and pointers can be declared on the same line. So you just have to be careful with that. If you do a pointer at the beginning, like this, a lot of people might think, oh, these are all pointers, because they might put the star here, which is also a valid way of writing it. So they see, oh, all these variables are pointers, but that's actually incorrect. Only a is a pointer, b and c are regular integers. So that's why I always attach the star like that. So here I have a pointer of a regular integer b, a regular integer c, and a pointer d. I also have here you can initialize a pointer equal to a variable on the same line. So I have an int a, and I can set pointer equal to the address of a on the same line. Obviously, you can't do it backwards. That's just a minor thing anyway. And here I just have an example, right? So I have two variables, a and b, and I have pointer 1 and pointer 2. And I'm just showing you how to assign pointers. I've already showed up here. But we're setting equal to the address of a, and just like regular variables, you can set pointers equal to other pointers, and that just copies the address that they hold. And it's always good practice to set pointers equal to null. Now, the reason for this is because if you dereference a null value, this can cause your program to crash. So typically, before you work with pointers, you usually check if they're null, and this helps avoid any seg faults in our code. So we know that if it doesn't hold an address, we obviously can't go there, right? So we just check to make sure that we can actually go there. And if we can't, then we usually say like, hey, you're not pointing to anything. So let's see. Here I just have more explanations for you guys. Once again, just like the last video, I have all the code that I'm showing on screen in the description below, so you guys can download it for yourselves. And here I'm just showing you that by changing the value in pointer, we can change the value in a. And I have this print statements here that I'm going to show you something quite nice. So here I can just show you a nice diagram. So here I set pointer equal to null, and I'm printing out that it's equal to a null memory address. So that's just a way you can check. And then here I have the status reports. So A is located at this address and it holds 55. B is at this address and holds 55. And the original pointer, this is its address. It holds the address of A, and it's pointing to this value, essentially. And here I have pointer 2, its address, where it's pointing to, and the value it holds, right? Because I did pointer 2 equals pointer 1, right? And I encourage you guys to fiddle around with a lot of these equal statements here to see how you can change these values. So like changing B by referencing pointer 2, or setting pointer 2 equal to pointer 1 and then changing pointer 2 and doing things like that. So I would encourage you guys to do that on your own time. And arrays. So a lot of people actually went over arrays a lot sooner than I thought. So I'm just going to do a pretty quick explanation because I think arrays at its basics are pretty well understood by everyone so far. But essentially it's just multiples of a data type held in one data type. So, or in one variable. So just like when we're creating an integer, we create like this box in memory. I do that quite a lot when I'm doing diagrams. Arrays are essentially just multiple boxes, one after another, right? So the way you do it is you have your data type and then your variable name and the amount of cells you want. That's what they're called. You might hear indices, indexes, whatever. And you do it by making the variable that you want. So in this case, I want an int array, the name of the array, and how long I want the array to be. Now, it's important to know that arrays start at 0, not at 1. So the first index is at 0 of the array, the second index is at 1, and so on. And if you want to reference a specific point in an array, you do the array name and the position in brackets. So the first point would be 0, so you do the array name of A, brackets 0, and that will change the value in the first point, or in the first cell. And here I just have how you would access specific points. So here I have question marks because you don't know what's inside of them right now. And then by doing these equal statements, you can see that this is our updated array now. And here I just have array cells go up to their length minus 1. So the final cell, even though it's 5 long, it's at position 4 essentially. So let's go ahead and compile this. So here I'm using a for loop to set every value of our array equal to just a multiple of 5, and then I'm printing out that value using an array. So typically when you're using arrays, you want to use for loops, because for loops are really easy to track where they start and where they end, right? And for loops typically start at 0, right? Which also happens to be where we start for arrays. So we can usually say that I starts at 0, I goes up to the length of the array, and that'll get us a piece of code that iterates for every single indice in our array. So here I have 0, 5, 10, 15, 20, and then just like these boxes are side by side in the diagram, they're side by side in memory. So here you can see an integer is 4 bytes, so you can see these memory addresses are 4 bytes apart, right? And this is in hexadecimal, so that's why you have C here, which is essentially equal to 12. So that's just something cool you can see. And then here I just have some math that you can do with arrays. And something also kind of important to know is that if you call what it's called the naked array name, so just array, it's a pointer to the base address of the array. So what I mean by that is it points to the first position in the array. So if I do something like this, I'm going to take the address. You can see that I get the same number, right? So the array, the naked array name and the first position are the exact same thing. So let's put this back. And there I'm just showing you the first and the last position of the array. So here I have a piece of code that uses an array to do some sort of math. So in this case, I'm finding the largest and smallest value and then the index it's at as well. So I have this array I've declared here. And to declare an array, I used a for loop to declare every single value manually, but you can also use curly brackets to do so. So let's say I have just an array, right? I can just set it equal to some amount of numbers and it'll automatically set the length of the array for me. I don't have to worry about putting a number in here. To calculate the length manually, we use size of the array divided by the data type of the array. So in this case, right, if you have size of an array, it returns the amount of bytes the array occupies, and then if you just divide it by one of the elements, right, so in this case, pretty much it's always size of 0, right, you get the size of the total array, or how many elements are in the array, I'm sorry. And here I'm just doing math to find the smallest position, right, so I'm checking if the ith position of our array is greater than our max, or if it's less than our max, because we're doing max and min in the same for loop, right? And then I'm just setting the values accordingly if they are. And here we get that we print out that the smallest value is 1 at index 5, which is correct, and that the largest is 7 at index 4, which is correct. So that's just some cool math. I suggest you guys take a look at this if you want on your free time. And just like arrays are essentially boxes side by side, you can also have 2D arrays, which are the same concept, but now in multiple dimensions. So here we have our 1D array, but here we have a 2D array. And where 1D arrays just had the amount of cells they have, 2D arrays have how many rows and how many columns they have. So I like to think of it kind of like an XY graph, which with each of these being a specific point in that graph. And just like 1D arrays, we can use the curly bracket notation to represent how many numbers we have in our array. So here I have a 3 by 3 array, and I'm manually declaring each of the rows here. So that's pretty cool. And here I have a very similar way of declaring and initializing the variables here. So instead of just having one bracket, I have 2. And here I'm using XY just because of the example I had earlier. And notice I'm using, just like I said, we use for loops for single arrays. We use two loops, right? If we want to use a 2D array. So here I have that the first loop typically keeps track of the rows, and the second loop keeps track of the columns. So here, instead of saying X, Y, you might see like rows and calls typically. I'm just going to keep it X, Y for simplicity purposes. And here I'm using a counter just to keep track of the position in the array. And I'm using post increment here because I'm starting at 1. So the value gets used first and then it adds 1. If you don't understand this, I recommend, once again, looking at the first video. So let's go ahead and compile this just so you can see what I'm talking about. So you can see that this array holds the values 1 through 9. And then I have another for loop here that just prints out those values. And here I have another for loop that prints out specific values in our array. So instead of doing ij, which represents our point in this xy graph, I'm doing I0. So I'm printing just the first numbers here, right? So 1, 4, 7. And I encourage you guys to change these values yourselves. So like 0 and j, and see what you get here. Things like that. And just see how you can change this to get different values. And just like you can do 2D arrays, right, to expand your dimensions, right, you can have as many brackets as you want, right? But eventually it gets hard to visualize, so typically 2 is the most you'll see. But here's an example of a 3D array. So instead of using 2 for loops, right, we have 3 for loops, one for the x direction, the y direction, and the z direction. And if I go ahead and run this, am I printing here? Oh, I didn't save. So here, it's harder to visualize, but you can kind of think of these like slices. So this would be behind this slice, and this would be behind this slice, right? And you can do this in 4 dimensions, 5 dimensions, etc., but that gets pretty hard to visualize pretty quickly. So typically we just stop at 2. But I'll leave this in here for you guys if you want to take a look at it. Okay, so let's talk about pass by reference functions. So up until now, we've only actually used pass by value. And a pass by value function means we pass it some sort of variable and we make a copy of that variable's value and then use that copy in the local function. So for example, right, in this void function I have here, I'm passing in int a and int b, and then I'm swapping those two values, right? But we know that this doesn't do anything in main if I call it, right? Because I'm only swapping the copies of these variables, right? Right? So essentially, you can think of this as I'm just giving a equal to 5, or x's value, and I'm giving b y's value of 10, right? And I'm then swapping a and b. I'm not swapping x and y in main, right? But a pass by reference function allows us to directly edit the values located in main, right? So now we can have a function that swaps and it actually does what we intend it to do, right? So pass by reference is typically faster because we don't have to create the duplicate variables, but it's also typically less safe because you are, at the end of the day, directly editing those variables. So let me just show you an example, right? So here we have the pass by value function. The logic's correct. It does swap them correctly, but because these aren't actually pointers, they're just changing copies. So we're not actually swapping the values in main. But here, right, using the pointers that we just learned about, we can set the values in these functions equal to the addresses of variables stored in main. So a and b, right now they're pointers, right, and they're holding the addresses of x and y. So when we swap these two, we are actually doing the correct output. So let's go ahead and open this and compile this. So here you see, before and after the pass by value example, x and y are the exact same. But after the pass by reference function, they do end up swapping in main. And here you can see that we're passing it the address instead of just the variable name. And here I'm using just different variables, so, but this could be x and y as well. And yeah, this is something you'll see a lot. Pass by reference and pass by value are definitely two things you want to remember. Just all you have to know is pass by reference. When you see the word reference, you're referencing something in main typically. And finally, we have 2 more here. So these might not end up being on your exam, but there are a few classes, I think one or two, that do go over these. So I want to just briefly mention them just in case you are in one of those classes that has something like this. So the first, I guess, ending topic I want to go over is structs. And structs allow us to have multiple members or fields. It just depends on whatever your professor calls it, to one variable declaration. And what that essentially looks like, it looks something like this, right? So we have our struct, and we have the name of what we want to call our struct, and then we have all the fields inside that struct. And there can be multiple fields here, right? So something like this. And we also typically tie structs in with something called typedef, which stands for type definition. And the way we use it is we use typedef, the data type name, and our new data type name. Now, we do that because structs, every time we want to reference a struct, we have to type struct, the variable name, and then whatever you want to call that variable in main, or wherever you're reference, or wherever you're creating a struct, right? So let's say I called this school, right? Or I'll just call it all lowercase. If I wanted to create a school in main, I'd have to do struct, school, and then let's say UCF, right? But if I use typedef, I can type typedef here. I can call this school, and then I can just type school UCF in main, as opposed to struct school. Now, if you're typing struct a lot of times, this can actually save you a lot of time in typing. I always do it just because I think it's cleaner. I don't like using struct every single time I want to reference a struct that I've created. So I just like doing this. It looks more minimal. And I'll leave this here just so you guys can see it. And here I just have an explanation again of typedef, the data type, and then the new data name. So struct, this whole thing is the data type. And then the new data type name goes afterwards with the semicolon. And it's also important, you do need the semicolon anyway when you're doing struct, because it's essentially like you're declaring a variable. So here I have a very basic example, and let me go ahead and run this. So this is called structs.c, and it just asks for basic information. So I'm just going to put in some random stuff. So John Johnson, who is a business major, and he's 20 years old. So we print out that our name is John Johnson, we're a business major, and we're 20 years old. And then I'm also showing you that just like arrays are next to each other in memory, fields in a struct are also next to each other in memory. So you can see these memory addresses are right next to each other. And here I have how you reference fields in a struct. So in this case, we're using a regular struct. So when I say regular, I mean a pass by value struct, or just a regular one. And to reference that, we use dots, right? So the period. So if I want to access the first name field in this struct, I do my person's name. So in this case, I'm using John, dot first name equals some sort of string, right? And here I'm using strings on purpose because a lot of people have problems with strings. So I'm essentially using these just to fortify that knowledge of strings for you guys. And then I just have a regular integer just because. And of course, I'm using typedef, like I said earlier. So here I have John.firstname equals getPersonInfo, and then last name and major. And then I'm showing how you would scan in regular integers or doubles or things like that. So in this case, I have getPersonInfo, which takes a string and returns a string. You don't really know or need to know what this function is doing. All you really have to know is that it's taking user input to take some sort of string, and it's returning a string. So in this case, I'm putting a string in John.firstname, John.lastname, and John.major. And here I have a printf that's asking for age, and it's taking scanf. Notice how I use the address symbol here. So I surround John.age with this address symbol. And the reason because is, just like arrays, the naked array name references the base address of the array. If you were to just do John.age, it would take the address of John, not John.age. So that's something you have to watch out for. And then here I have a function that prints out all of the fields in our struct. And here I'm passing it a struct. So in this case, I'm passing it John. And then if we go to this print statement, you can see I'm passing in a person and then input person. So this might start looking a bit weird just because it's a data type that we've created, but know that this functions just as any other data type would. It's not something you're unaware of or you haven't seen before. It's just a different way of writing it. And just like these are strings, right, I can reference them using conversion codes just like I would any other string. So here I have input person dot first name, dot last name, dot major, and dot age, right? And I use the right code and everything. And just like we showed earlier, it works. So I recommend, for example, adding different things here. Try adding an int array into a struct and see how you can scan into that. That'd be a pretty nice challenge. But yeah, this is only for a few people, and I doubt they're going to even use strings, but just thought I'd introduce it just in case. And the very last thing is memory allocation. So this uses pointers like we learned earlier, except we don't actually know the name of the variable we're referencing. So let me explain. So we've always dealt with static variables, which means we create the variables ourselves and we know where they are, we know what their name is. But dynamic memory allocation allows us to create variables without the variable name. And the way we do that is we access its location in memory rather than the name itself. So we're actually just referencing it by using its address instead of its name. So the basic layout is using something called Malloc, which stands for memory allocation. So we do our data type, our pointer to our variable name, because these have to use pointers, because Malloc returns a pointer to an address, right? And then we do Malloc size of whatever data type we're using. So here I have just an explanation, and it's a pretty, I'm just going to read it out. So Malloc takes the size of something, right? So in this case, a data type, and creates space for it in memory. And then Malloc returns the address it creates. And we want to use size of because when we create a variable, we want to have the exact size of that variable. And variables might be different sizes across different operating systems. So if we just did size of, or if we just did Malloc 4, right, that'd work for my operating system, but let's say another operating system uses integers as 8 bits or 8 bytes or 2 bytes, right? Suddenly my Malloc function doesn't work anymore. So always use size of. And then Malloc is nice because it allows us to use reference functions very easily. Let me change that. However, the most notable problem of Malloc is that it's really easy to introduce something called a memory leak. And to avoid memory leaks, we use another command called free, which essentially removes the address that we just created. So let me explain what a memory leak is in a little bit. So here, I just have a basic pointer showcase just in case you're looking at this file by itself, but you should know how pointers work, so I'm not going to explain too much. This is just printing out all the values in these two pointers and showing how changing the pointer, you can actually change the value that it holds the address of. So let me go ahead and run this. So that's that example. But then down here at line 49, we actually start using memory allocation. So I do pointer equals Malloc size of int. So now our diagram that used to look just like these two boxes, now we have this third box and it doesn't have a variable name, just has the address. And now our pointer holds onto this address here. So if we want to change this box, we have to change pointer. So when I do star pointer equals 1, 2, 3, now this is what our updated drawing looks like. And here I'm printing out the values of pointer. So previously, pointer held on to the address of A. And now it's holding on to this random address that we've created. And here I'm freeing pointer so I can create a new pointer address. Now, I said every time you use Malloc, you want to free, and that's correct. Every time you use Malloc, you want to have an equal amount of frees in your code. So here I Malloced, and before I Malloc again, I free it, because if I Malloced again, I'd create another box, and I'd lose access to this box, right? Because now my pointer would be pointing to the fourth box, essentially, here in this diagram, and nothing would be able to access this third box, and that's called a memory leak. So let me show you what happens here. So here's the diagram I was talking about, and let me change this to 71. So if I were to compile this, and then I use a program called Valgrind, which checks for memory leaks for me, You see I have all heap blocks were freed and that there's no leaks because I freed correctly. And I'm also freeing at the very end before I finish compiling my program. But if I delete this and I introduce a memory leak into my program, now you can see I've lost 4 bytes, right? And an integer's 4 bytes, so that makes sense. And this becomes a problem if you have something that's being mallocked, let's say, thousands of times, right? And you're never freeing it, you're going to lose thousands of bytes of memory. And over time, if you have a large enough function, that can actually be really detrimental to the runtime and the memory size of your program. And that's pretty much it, I think, for exam 2. I expect there to be a lot of things about for loops still and if statements, just like on exam 1. But overall, I think the topics for exam 2 should be relatively simple. A lot of it is just formatting, and just because things are new doesn't mean they're difficult. I feel like people will psych themselves out, especially with pointers. I feel like that's probably going to be one of the most difficult things to grasp, but definitely just try and do as much work with them as you can. Don't psych yourself out too much. Just know that when you're using pointers, you're using addresses instead of variables directly. You're essentially using a variable just indirectly, if that makes sense. Make sure you never dereference a null pointer. That I can almost guarantee that's going to be asked somewhere on your exam. Yeah, I think that's pretty much it for me, though. If you guys have questions, feel free to email me. Also, I have my sessions on Monday, Tuesday, Thursday from 4:30 to 6:30. Highly suggest going out to those. And yeah, I wish you guys best of luck on your second exam. Hopefully this video was helpful, just reminding you about a few tips for each of these topics. And yeah, I hope to see you at my next session.